This video will show you how to rationalize the denominator. So to be fully simplified means that there's no radical in the denominator. So for example, your simplified radical cannot look like this. The process of eliminating the radical is called rationalizing the denominator. And so you need to think about, how do you eliminate a radical? So what's the inverse operation of a square root? So if we were going to solve this example, to get rid of this square root, I would square this. And so the opposite of square root is squaring. And so that's important to remember. So why is it important? So we just said, if I want to get rid of the square root, I'm going to square. Squaring literally means taking something times itself. So square root of 2 squared is really square root of 2 times square root of 2. Square root of 2 times square root of 2 is really square root of 4. And the square root of 4 is actually 2. And so if we think about what happened from the beginning to the end and kind of eliminate those middle steps, square root of 2 squared is just 2. And so this radical has disappeared, which is what we want to happen when we're rationalizing. So here's some examples. So to figure out square root of 5 times square root of 5, I can most definitely write out the middle step. So the middle step is, it's square root of 25. But the square root of 25 is really just 5. And if you look, what's kind of happening is whatever the radicand is all that's left over. So you don't really need to include these middle steps. So for the next one, square root of 17 times square root of 17, all that will be left is this radicand, which is 17. So square root of 529 times square root of 529 will just be 529. Here's the process to rationalizing the denominator. You want to reduce the coefficients and radicands if possible. So you're looking at those fractions that are created, and if you can simplify them, do that. If a radical remains in the denominator, you want to multiply the numerator and denominator by that radical that's in the denominator. So that's the part that's actually called rationalizing. And then you're just going to continue simplifying as needed. So essentially after each step, you want to check your coefficients, can those be simplified? You want to check your radicals that are at fractions, can those be simplified? And then you want to check your radicals by themselves, can those be simplified using your perfect square factors? Let's look at what this would look like. So here's your first example. So from our lesson on division, we know that we want to rewrite this as a radical in the numerator and denominator. Next, I'll check, since these are both in a radical, can the fraction itself be simplified? So think about 4 over 6. 4 over 6 is really just 2/3. Since these are all in radicals, we can do the same thing. So this can be rewritten as square root of 2 over square root of 3. Then, to be fully simplified, we can't leave a radical in the denominator. So we want to rationalize. And we do that by multiplying square root of 3 by itself. But whatever we multiply on the denominator, we also have to include on the numerator. Then we're going to multiply across our numerators. So square root of 2 times square root of 3 is square root of 6. Square root of 3 times square root of 3 is just 3. So think back to that very first slide. Remember, square root of 3 times square root of 3 was square root of 9, and square root of 9 is really just 3. So I kind of just skipped this middle step. Now, I don't have any fractions I can look at because I can only simplify coefficients, and I can only simplify things that are in radicals, and there aren't any that are matching up right now. So lastly, I just want to look at square root of 6, and I want to think about my list of perfect squares. So 4, 9, 16, 25. Can square root of 6 be divided by any of these numbers? And the answer is no. So this would be my final answer. Example number 2 can be solved 2 different ways. The first way is, maybe I look at this, I see that I have this fraction created, and I notice I can divide both of them by 2. So I end up with square root of 9 over square root of 2. The square root of 9 is really 3. And then I notice I have this square root in the denominator, which I'm not allowed to have. So next I'm going to rationalize the denominator, and I do that by multiplying it by itself. Whatever I multiply by on the denominator, I also need to multiply in the numerator. I multiply across my numerators. Since 3 is not in a radical, they can't be combined, so they're just going to sit next to each other. Across the denominator, square root of 2 times square root of 2 is just 2. And then just double checking, can I simplify further? So can this fraction be simplified? No. 3 over 2 is as simplified as it can get. I also want to check this radical, so think about your perfect square list. 4, 9, 16, 25. Can 2 be divided by any of those numbers? The answer is also no. So this would be our final answer. Another way you can approach the same problem is maybe immediately you recognize that square root of 4 is actually a perfect square and it's just 2. And then you notice that you could simplify square root of 18 because one of its factors is 9. So square root of 18 could be written as square root of 9 times square root of 2. Square root of 9 is actually just 3. Again, double checking, can 3 over 2 be simplified? No. Can square root of 2 be simplified? No. And so this would be the final answer. Notice that no matter which method I used, I got the same answer. Starting example 3, I'm going to start by seeing if I can simplify this fraction. I can because I could divide both of them by 2. If I divide them both by 2, I end up with 2 square root of 5 over square root of 4. The square root of 4 is actually just 2. This 2 over 2 would cancel out, leaving me with square root of 5. And then checking my list of perfect squares, I see I can't divide 5 by any of those numbers, so this is the final answer. In example 4, I would start by checking this fraction, 5 over 18. 5 over 18 can't be simplified any further, so there's nothing I can do with that. So then I realize that I just need to rationalize my denominator. So I'm going to start by multiplying by square root of 18 over square root of 18. I multiply across the numerator. 5 times 18 is square root of 90. Square root of 18 times square root of 18 is 18. Then I want to think about my perfect square list and see if there's any of those that will divide into 90. So when I think about this list, I realize that 90 can be written as square root of 9 times square root of 10. The square root of 9 is actually 3. And then continuing, I realize that 3 over 18 can be simplified to be 1/6. So this is really 1 square root of 10 over 6. However, kind of like we don't write 1x, it's not really necessary to write 1 square root of 10. So square root of 10 over square root of 6 is sufficient. Then I want to double check this square root of 10. Can I divide it by any of my perfect squares? And the answer is no. So this would be my final answer. For example 5, I would check the fraction first, 2 over 3. It can't be simplified, it's already as simplified as possible. So next I just want to start by rationalizing the denominator. And I do that by multiplying by square root of 3 over square root of 3. Multiplying across the numerator, square root of 2 times square root of 3 is square root of 6. Square root of 3 times square root of 3 is 3. Next I would check, do any of my perfect squares go into 6? So 4, 9, 16, 25. No, I can't divide 6 by any of those. So this is as simplified as it gets. For this example, I would need to start by rationalizing the denominator. I multiply across the numerator. 1 times square root of 27 is 1 square root of 27, but I don't really need to write down the 1. Square root of 27 times square root of 27 is just 27. Next, I would want to check, can I simplify square root of 27? So focusing on my list of perfect squares, I realize I can divide 27 by 9. So I'll rewrite it as 9 times 3. Square root of 9 is actually 3. And then I want to double check this fraction that's created. So 3 over 27. I can divide both the numerator and denominator by 3. And I end up with 1/9. So I end up with 1 square root of 3 over 9. But I don't really need to write the 1 out in front, so we'll just write square root of 3 over 9. To double check one more time, can square root of 3 be divided by any of my perfect squares? And the answer is no. So this is the final answer. For example 7, I start by checking this fraction, 6/5. It can't be simplified. So instead, I'm just going to rationalize right away. I do that by multiplying by square root of 5 over square root of 5. If I multiply across the numerator, I can't multiply 2 with 6 and 5 because 2 is not in a radical. So I'm just going to carry it over. Square root of 6 times square root of 5 is square root of 30. Square root of 5 times square root of 5 is just 5. I can't simplify 2/5, so now I'm going to check my square root of 30. Can I divide square root of 30 by any of my perfect squares? And the answer is no. For my last example, I checked to see if I can simplify 8/7, and I can't. So I'm just going to start by rationalizing my denominator. So square root of 7 times square root of 7. I multiply across the numerator. Square root of 8 times square root of 7 is square root of 56. Square root of 7 times square root of 7 is just 7. Then I want to check the numerator. Can I divide square root of 56 by any of my perfect squares? And I can. I can divide 56 by 4. So 4 times 14 would get me 56. The square root of 4 is actually 2. I can't simplify 2/7, so I'm good there. And then I just want to double check 14. Can 14 be divided by any of my perfect squares? And since it can't, this is the final answer.